Hi, today we're going to be talking about inverse functions in our lesson 1-8, and I'm asking you to look to begin with at the two formulas at the top of the page. Some of you might recognize them. This one that's called f of x, this function takes Celsius temperature as input and it produces the matching Fahrenheit temperature. This one, on the other hand, gives you a Celsius temperature if you put a Fahrenheit temp in as its x. So these two are probably the most familiar inverse function pair that we know. They're the ones that we see sometimes as we go through school. And to begin today, I'd like to just say that a function and its inverse, really folks, what they do is they undo each other. And you can see that as you look at these two functions. In one, you see a minus 32. In the other, you see a plus 32. In one, you see a multiplication by 5/9. In the other, you see a multiplication by 9/5, the reciprocal. So those two functions, they kind of undo each other. And to show you what we mean, we're going to just work a little bit with the compositions of these functions. You'll remember from the previous lesson that this notation says find f of c of x, which means use c of x as input to the f function. So c of x is this business, 5/9 times the quantity x minus 32. We are going to replace that in the place of x in this function. So to do f of c of x, then we got to be thinking we need 9/5. The x here is going to be this whole business, so it's 5/9 times x minus 32, and then back from here we are supposed to add 32 to that result. So let's do a little bit of math here, and I would just point out to you that there is multiplication here and here, so I'm going to put that parenthesis there. Here and here is addition, and you know the multiplies have to come first and you go left to right. So as you look at these things, the 9s and 5s, they cancel each other out, or a number times its reciprocal is 1. And really, this is a fancy long way of saying x minus 32 plus 32. And we simplify that further, we get back to, guess what? Just x. Okay. That's kind of an interesting little phenomenon. I wonder if it works the other way. So this says find c of f of x. So now we're going to do this function, but in place of its x, we're going to put all this business. So let's see how that one works out. 5/9 times x, and x is now this. 9/5 x plus 32. And then, so now we've done the replacing, and then this function has a minus 32 on it. Okay, so now I'm looking at this. Inside the parentheses, there's some work that we can do. We've got a plus 32 and a minus 32. So when we simplify this, we're looking at 5/9 times 9/5 times x. And amazingly enough, there's that number and its reciprocal again, folks. That's equal to 1 when you multiply, and all you get out of there is x. And this, folks, is really an interesting phenomenon. When you compose a function with its inverse, it will always, always come back to x, always get x. So you can use this little process to decide whether or not two functions are inverses of each other. You compose them both ways. Compose both ways, f of g, g of f, and simplify, then check to see if what you get is x. Check to see if it simplifies to x. That's pretty cool. Okay, my handwriting gets a little bit weird when I get happy, but this is neat. So this says that we're supposed to apply that, I think. We're going to show that f of x equaling 4x minus 7 and g of x equaling x plus 7/4 are inverses of each other. So the rule says, or the process says, you compose both ways. So I'm going to do f of g to start with, f of g of x. and that means that I'm going to put the g function in place of x in this one. So I'm going to have 4 times, and then whatever was in g of x, that's x plus 7 over 4 minus 7. And do the work. Multiply takes precedence over the adding, and you can't simplify inside the parentheses. But 4 over 1 times something over 4, the 4's cancel out, and you're going to get, so they divide into each other. It goes once in each place. X plus 7 minus 7, which is x, and that's good news. It should work the other way, so when we do g of f of x, we should get x again. This time we're going to put the f function in place of the x here. So this one would be 4x minus 7, that's taking the place of that, plus 7 all over 4. Now the fraction bar is a big grouping symbol, so whatever is up here has to be simplified first if possible, and you can see that it is. We have a minus 7 and a plus at 4x over 4, which is the same thing as x, and look at that. Both ways simplify to x, so yes, they are inverses of each other, and that, my friends, is pretty darn cool. Alright, we want to just review quickly how to find the inverse of a function, and this is something that we talked about in our prerequisite chapter, but we'll review it here just really briefly. In equation form, to find the inverse of a function, you switch x and y and then solve for the new y. Switch x and y and solve for the new y. And I'll put new in quotes, kind of. Alright, so if we're going to find the inverse of 2x plus 7, and we realize that f of x means y, okay, it says we switch x with y. So we're going to say x equals 2y plus 7. We're going to solve for the new y. So we subtract 7. X minus 7 equals 2y. We divide by 2. X minus 7 over 2 is the same thing as y. There's the inverse. Alright. You try it now. Find the inverse of y equals 4x cubed minus 1. Pause that video. See if we get the same thing I do. X equals 4y cubed minus 1. I add 1, so x plus 1 equals 4y cubed. I divide by 4. X plus 1 over 4 equals y cubed. I come out here because I'm out of room. Take the cube root of each side. Y would equal cube root of x plus 1 over 4. Nifty. Alright. In a graph or a table of values, switch x and y values to find the inverse. You still switch x and y. And I'd like to demonstrate that with this little function, f of x equals 2x minus 1. I'm going to use the input values, negative 2, negative 1, 0, 1, and 2 to get my values for f of x. When x is negative 2, y will be negative 4 minus 1, that's negative 5. When x is negative 1, that's negative 2 there, minus 1, negative 3. When x is 0, y is negative 1. When x is 1, 2 times 1 is 2, 2 minus 1 is 1. And when x is 2, let's see, 4 minus 1, 3. So we have a set of points to plot for our function f of x. Negative 2, negative 5, negative 1, negative 3, 0 and negative 1, 1 and 1, 2 and 3. There we are. There's our function. Now, according to my rule, to get the inverse, we switch x and y. So to graph f inverse, the points that we'll want are negative 5 and negative 2, negative 3, negative 1, negative 1 and 0, 1 and 1, that points on both the function and its inverse, and then 3 and 2. And let's see what we get there. When x is negative 5, y is negative 2. That's here. When x is negative 3, y is negative 1. X of negative 1, y of 0. Here's that 0.11 that's on both. And then 3 and 2. So the inverse of our line is also a line. And one thing that you might notice, the graphs of a function and its inverse, folks, they are reflections of each other over the reflection line y of x, or y equals x, reflects over y equals x, because that's exactly what you did was switch x and y, so you get that reflection. Very interesting. All right, here's one we'll kick it up a notch, and let's do the same thing, only this time the function's a little bit more complicated. F of x is 1/2 of x squared, so the x's that we're interested in, 0 we want in the middle, and I am going to go with my usual negative 2, negative 1, 0, 1, and 2. When x is negative 2, negative 2 squared is 4, and half of that is 2. When x is 1, well, negative 1 squared is 1, and yeah, that's a half. When x is 0, we get 0. When x is 1, well, we still get 1/2, and when x is 2, half of 4 is 2. So there's our function, negative 2, 2, negative 1 and 1/2. This is going to be a parabola, but it's going to be a little wide one because that a value is 1/2. That widens things out. So here's our original function. Good. To graph the inverse, or to find the inverse, we switch x and y. So the point 2, negative 2 will be on the inverse. 1/2, negative 1 will be on the inverse. 0, 0 should be on the inverse. 1/2 and 1, 2 and 2. All right, let's plot those and see what we get here. When x is 2, the inverse is at negative 2. X of 1/2, inverse is at negative 1. Then 0, 0, 1/2 and 1, and 2 and 2. All right, so there's the inverse function. Except I said function. Folks, is it really? Because there are vertical lines that hit this more than once. In fact, when x is 2, there's more than one value there. This is not a function. No. How can you tell from the graph? It doesn't pass the vertical line test. Doesn't pass the vertical line test. How can you tell from a table? Well, in the table, x's are repeated. There are x's that are repeated, and they don't show up with the same y. So some x's have 2 y's. Okay. In cases like this, we can make sure that our inverse will produce a function when we invert it if we restrict the domain of our function. So if we restrict the original domain, so the domain of f of x, we can get an invertible function. For example, if we restrict the domain of f of x to only, and folks, I would ask you to think about this. Since we know this is a reflection over the y equals x line here, then if we make the domain on the black function be only positive, then we get this positive branch of the square root function. So if we restrict the domain of f of x to only x greater than or equal to 0, the inverse does count as a function. This black half, here's its mirror image. So by restricting the domain of the original, we can force the inverse to be a function. All right, let's see if we can't just put it all together here, and let's see what happens. We want to find the inverse of f of x equals negative 3x plus 2. According to the thing, we switch x with y, so we're going to think x equals negative 3y plus 2. We're going to work backwards to get that y by itself, so we got to subtract 2, x minus 2 equals negative 3y, divide by negative 3, and I'm going to move the y to the other side. Y will equal the quantity x minus 2 over negative 3. Or you could rewrite that as negative 1/3 x plus 2/3. Okay, very good. Verify that they are inverses. So if I do f to this, I ought to get back to x. Let's see. If I do negative 3 times what I just said was the inverse, actually let's leave it in this form. That'll make the work a little easier for us. X minus 2 over 3 over negative 3. And then the rest of that was plus 2. Okay, we know we can't simplify here, but this multiplication has to happen before this add. The negative 3's cancel. We get x minus 2 plus 2, which is x. So that's good. Now we go the other way. We put the f function into the g1, and we think to ourselves, okay, it calls for x minus 2, so we're going to put in negative 3x plus 2 minus 2 all over negative 3 equaling, well, now we simplify. On top, the 2 minus 2 goes away. Negative 3x over negative 3 equals x. Yes, they're inverses. Yes, they are. Alright, graph the function and its inverse. Okay, I'm going to graph my f of x over here. I'm going to use the x as negative 2, negative 1, 0, 1, and 2. Once I find values for y, I'll graph the inverse over here, so f inverse of x. And when x is negative 2, negative 3 times negative 2 is 6. 6 plus 2 is 8. Negative 1. Negative 3 times negative 1 is 3. 3 plus 2, 5. When I put 0 in for x, I get 2. When I put 1 in for x, that's negative 3 plus 2, negative 1. When I put 2 in, I get negative 6 plus 2, negative 4. I'm going to plot those points, the ones that I can. And let's see, negative 1 and 5 up here, 0 and 2, 1 and negative 1, and 2 and negative 4. So here's f of x. Alright, then to get the inverse, I'm going to just invert the points. So 8 and negative 2, I'm not going to be able to graph that one. 5 and negative 1, 2 and 0, negative 1 and 1, negative 4 and 2. And let's see what we get. 5 and negative 1 over here, 2 and 0 here, negative 1 and 1 here, negative 4 and 2 there. And our line that is the inverse right here, and sure enough it looks like they are a reflection over that y equals x line. Alright, so we have our inverse. Very good. That's the end of our lesson today. I would ask you to try that you-try exercise as quickly as you can, and we'll talk a lot about inverts. Oh, I forgot to answer this question. Is the inverse a function? What do you think? All lines are functions, except for x equals lines. So, except for vertical lines. Alright, as we were saying, try that you-try, and we'll see you in the next class period. Bye-bye.